Hi, welcome. Today we have a really interesting proof, so let's get right to it. We want to prove that if we take all n-digit integers and sum them up for n greater than 2, then the result we end up getting is a number which has the following digits. 494 that lead the number, followed by a sequence of 9s, and there are n minus 3 of those, followed by the 5 and 5 as the next digits, followed by some trailing zeros, n minus 2 of them. Well, what does that even mean? By way of example, let's look at what's going on here. Let's take a look at all 3-digit integers. The smallest 3-digit integer would be 100. But that's just 10 squared. The largest 3-digit integer would be 999. But that's just one less than 1,000, and 1,000 is a power of 10. So we have 10 cubed minus 1. Now, starting at this smallest 3-digit integer, 100, let's then add the next one, 101, and then the next one, 102. And we'll keep going all the way to 999, and therefore add all 3-digit integers together. What would that give us? Well, we would have 100 plus 101 plus 102 all the way up to 999, this number here, this integer. Well, you could then try this for 4-digit integers, and the first one would be 1,000 or 10 cubed, and the largest would be 10 to the power of 4 minus 1, which is 9,999. And then we could write out a series like this for the 4-digit integers. But it's probably pretty clear that to generalize this statement for any n-digit integers, what we have is the following. We would take the lowest n-digit integer. So if you notice, for 3-digit integers, 10 to the power of 2 is the smallest. This exponent is one less than the type of numbers that we're dealing with. So we have 10 to the power of n minus 1. Then we would add the next number above that. Then the next one above that. All the way out to the largest n-digit integer. Taking this as our example, notice it's this power of 10 minus 1. This power of 10, the exponent matches the type of numbers we're dealing with. So 3-digit integers in this case, so a power of 3 here. So this is our generalization. But if we add 3-digit integers, there's only so many of those. If we add 4-digit integers, there'll be more of those. If we add all 5-digit integers together, there'll be even more of those. So how many terms are we adding up here? Well, for an arithmetic series, the number of terms is given by the following. We'll take the nth term of the series. In this case, there it is, the last one. Equal to the first term of the series. Here it is, the smallest one. And then here we have n minus 1. N is the number of terms that we're looking for. Times, well, d is simply the common difference between neighboring terms. Neighboring terms differ by 1. Again, using 3-digit integers as an example, 100 plus 101 plus 102 plus 103, etc. Each of those neighboring numbers or integers differ by 1. So this is just 1. So what does this give us? Well, we have a -1 on this side and a -1 on this side, leaving us with 10 to the power of n minus 10 to the power n minus 1 equals n. But we can clean that up. If we factor out a 10 to the power of n, we get 1 minus 10 to the power of, well, subtract this minus this, we get -1. But what we have in brackets is 1 minus a tenth. That's 9/10. But this 10 to the power n divided by this 10 gives us 10 to the power n minus 1. So now we see that there are this many terms in this series. So let's go to the next board and continue. Okay, here we are back at our board and we've summarized where we left off. Here's our series. Here are the terms we're adding up. There are this many of those terms. But what exactly does this add up to? Well, for an arithmetic series, the classic formula for the sum of the series is half n times 2 times the first term plus n minus 1 times d. So let's substitute what we already know. The number of terms n is this quantity. This first term of the series is 10 to the power n minus 1 plus, here again is n, so 9 times 10 to the power n minus 1 minus 1 times d again, which is just 1 as we mentioned before. And let's see how we can clean this up. Here we have 2 times this power of 10 plus 9 times that same power of 10. That's 11 of those powers of 10. And now we're going to pull a clever trick. We're going to multiply this quantity on the outside by unity, or 10 over 10. And the utility of that will become apparent very shortly. What we can do from here is take 9 times 10 divided by 2, which is 45. And then we still also have this power of 10 divided by the green 10. So that gives us 10 to the power of n minus 2. And then what's in brackets? From here, we'll expand this. This quantity multiplied to this quantity, well, we can take the 45 times the 11 is 495. And also this power of 10 times this power of 10, add the exponents, 2n minus 3. And then distribute this to the minus 1. So what can we glean from this right now? Well, this power of 10, the lowest it can be is when n is 3. So 2 times 3 minus 3 is 3. And so this power of 10 gives us 1,000. 495 times 1,000 is 495,000. And then we're subtracting off from that. What's the lowest possible quantity we can subtract off from that? Well, here, this lowest power of 10 would occur when n is 3. So 10 to the power 3 minus 2 is 10 to the power 1, or 10. So 45 times 10 is 450. So 495,000, subtract 450, 50 will be 494,000 and change. Now 494, that's this. So how can we incorporate that into this line of our work? Let's take 495 and break it up as 494 plus 1. And perhaps these digits of 5, we can do something about that. This 45, why don't we write it as 100 minus 55 times 10 to the power n minus 2. Now what we obtain is the following. Let's expand 494 times this. 1 times this. And now 100 is 10 squared times this. So we're going to add the exponent of 2 from 10 squared to this exponent. So we're left with just n. And then this negative 55 times this power of 10 is plus 55 times n to the minus 2. One more touch up here. These two powers of 10, let's factor out 10 to the power n. What does that leave us with? Well, this subtracts n, and this leaves us with 1, and 55 times 10 to the power n minus 2 at the end. Just rearranging this power of 10 to put it on the outside here. We obtain the following. And so notice we have this power of 10, this power of 10, and that power of 10. So here we are at the next board. Let's take a look at some cases for different values of n. First, let's look at n equals 3. When n equals 3, let's add this plus this quantity. When n is 3, this is 10 cubed, so 494 times 1,000 is 494,000. Then to that we're going to add what we obtain here. Again, 10 to the power 3 minus 3 is 1 minus 1 is 0. And then we're going to add, well, 10 to the 3 minus 2 is 10 times 55 is 550. So there's our sum of all 3-digit integers. How about for 4-digit integers? Well, this is 8 minus 3, which is 5. So 10 to the power 5 times 494 is 494 with 5 trailing zeros. Then to that we're going to add this amount. Well, when n is 4, we get 4 minus 3, which is 1. So 10 minus 1 is 9. But we're always going to get 9s here, just to foreshadow, because here's a power of 10, right? 1,000, 10,000, 100,000. And when you subtract off 1, you're left with just a string of 9s. So here in this case, we get 10 to the power 4 minus 3, which is 10 minus 1 is 9, times 10 to the power 4. That's 9 with 4 trailing zeros. And then over here, when n is 4, we have 10 squared, which is 100, times 55 is 5,500. Adding these up, we get 4949550. In the n equals 5 case, let's see what happens. This quantity, we have 10 minus 3 is 7. 10 to the 7 times 494 is 494 with 7 trailing zeros. To that we'll add what this quantity gives us. So here, when n is 5, we get 10 squared minus 1 is 99 times 10 to the power 5. So that's 99 with 5 trailing zeros. And here we get 10 cubed, which is 1,000, times 55, so 55,000. Adding these all up gives us and so notice what's happening here. From the n equals 4 to the n equals 5 case, we'll make it a little clearer than looking at this case to this case. This quantity here has 5 trailing zeros. This quantity here has 7. And by the way, this one over here has 3. So the number of zeros, trailing zeros here to here to here is increasing by 2. So we have an extra 2 zeros every time we take a step forward to the next value of n. As well, down here, we gain an extra trailing zero. Even here, we have from 1 to 2 to 3 trailing zeros. So we gain an extra trailing zero. Now what happens to these values in the middle is, well, the pattern from here to here is not so obvious. But from here to here, what ends up happening is we gain an extra 9. So this 9 is extra at the front, and this 0 is gained at the back. So every step of the way, we will now gain an extra 9 and an extra 0, a leading 9 and a trailing 0. And so what we notice, to say this informally, is every time we gain 2 trailing zeros in the 494 term, that makes room for an extra 9 and a 0 to fit in this digit's place and the next digit's place right after this 4. And with a few more examples looking at subsequent values of n, we see that that's true. We always make room for an extra leading 9 and a trailing 0. And that extra leading 9 always begins right after this digit's place of the 4. And down here, the 5, 5 always begins in this digit's place right after that last 9. And so when we add up this quantity plus this quantity plus this quantity, according to this pattern we've just revealed, we do in fact obtain a sum that takes on this format. What is the format? Well, let's see. When n equals 3, we have 494 leading, then n minus 3 nines, but in the first case n is 3, so we have no nines, followed by the digits 5, 5, and then n minus 2 trailing zeros. So 3 minus 2, that's 1 trailing 0. In the n equals 4 case, 494 leads the number, followed by 4 minus 3 or 1 9, followed by 2 digits of 5, followed by 4 minus 2 or 2 trailing zeros. And here, 494 leads the number, followed by 5 minus 3, or 2 9s, and then these 2 5s, followed by 5 minus 2, or 3 trailing zeros. And so this pattern does continue, and we do obtain this result when we add all n-digit integers together. And that completes the proof. I hope you enjoyed. Thank you.